Okay, we're going to continue on here with chapter one. So last time we got into it a little bit. We talked in general about a little bit about chemistry. We talked about matter and again the different states of matter, where we have solid, liquid, and gas. We also talked about sort of the transitions that occur between these different states. Again, solid to liquid is our melting process, our freezing process going in the other direction, our evaporation as we go from liquid to gas, gas back to liquid, our condensation, solid directly to gas, our sublimation, and gas back to solid, our deposition. So we talked about the idea that a lot of chemistry deals with matter and as they change states from solid to liquid, and also the idea of energy associated with that. We had our processes, for example, is going from solid to liquid to gas. Those are all processes, as we talked about, which involve energy being absorbed. And again, as we talked about, that was commonly referred to as an endothermic process in chemistry. Again, we don't talk extremely a lot about energy, but it does pop up a lot because, again, they assume we kind of did that chapter that we're going to skip this semester, and you'll take care of it in the next semester. As we go from gas to liquid to solid, again, we need everybody to basically release that energy as they're flying around with a lot of energy. As they release that energy, they're going to slow down. And as they sort of collide with each other, they will no longer have enough energy really to escape each other. And they'll kind of collapse into the liquid phase. And as energies continue to remove, then they'll sort of lock themselves into the solid phase. And again, those are all processes, as we talked about, where energy is released. And that is what is known as being exothermic in chemistry. In general, when you talk about energy, and again, energy sort of calculations, or you see energy calculations, again, a positive value typically represents an endothermic process. If you see a negative value for energy, that is typically a exothermic type process that's occurring. We talked there at the end about scientific method, and again, usually starts with observations leading to some type of hypothesis that could be tested. You do some type of experimentation, which again, oftentimes will lead to more observations. And again, hopefully we get to a point where, as we talked about at the very end, we will end up with something that's either, sort of a law or a theory. Remember that a theory is really something that does sort of explain what's going on, but it can be sort of modified if you want to think about it that way. It can be later maybe proven not to be correct in all aspects. It can be sort of revised in that sense. A law, on the other hand, is something that pretty much always happens the same way, no matter what the situation is. It's pretty constant sort of thing that will occur. Any questions on any of that stuff there? All right, so we're going to continue on here. We're going to get really now into sort of the atom and talking about some experiments that led us to a better understanding of the atom and the different parts of it here. So we'll kind of cruise through some of this. So early on, a lot of stuff was done by philosophers, and the idea of chemistry, Robert Boyle, Boyle's law, all that good stuff there was performed. A lot of quantitative thinking experiments. Um, and really, when we think about sort of laws, as we mentioned, again, those are things that no matter what situation is, will always be the same. So, for example, the law of conservation of mass, again, we don't create nor destroy mass. Give it a click.
Again here for a quick chemistry demonstration. This is going to be law of conservation of mass, or law of conservation of matter, depending on which way you like to talk about it. So the law basically says that in any chemical reaction, matter or mass is conserved. It cannot be created or destroyed. That means that when you start a chemical reaction, the mass before and the mass after should be the same. I've got some calcium chloride here, which I'm going to use to place in the Erlenmeyer flask. Exact amounts are not necessary in this demonstration, so that's probably about enough. place that on my balance here. In order to have a chemical reaction, we need two chemicals, so I am also going to add some sodium sulfate. I'm going to add it in this test tube. About half full should be good enough. So I'm going to place the test tube inside the Erlenmeyer flask. Notice that the two chemicals are not mixing yet. I'm also going to use a stopper to stop up the top of the Erlenmeyer. And we are now going to note the current mass on the balance. You should be able to read that. It says 369.1 grams. 369.1. Now, in order to get this reaction to occur, I've placed the stopper on the flask. That way, if there's any gases created, it won't allow them to get out. Also, in order to get this, in order to get these two solutions to actually mix, I have to flip it upside down. So I'm going to flip it upside down, carefully agitate the two mixtures. The two solutions actually mix. And you can see there's a pretty startling reaction here. When I place this back on the balance, what you're going to notice is that it's the same mass as before, plus or minus a decimal place. 369 point.
In a chemical reaction, we basically just break bonds. So we really don't change any elements or anything like that. So again, if you started, for example, with those, say, 6 carbons, you're going to end up with those 6 carbons on the other side of the reaction there. It's going to be in different sort of locations. In that example, we had a couple of sodiums. They're going to still be there on the back end of the reaction as well. Again, they may just be bonded to different things. The law of definite proportions was another sort of important law. Is a given compound always contains the exact same proportion of elements by mass. So again, you could think about something like water. And in water, there's basically 2 hydrogens for every 1 oxygen. And in terms of mass here, that's basically about 2 grams for every, it looks like a 10, but that's oxygen. Basically 16 grams here. So as you can see, in the case of this is basically a 1 to 8 relationship in terms of the grams of hydrogen to oxygen. And if you look at other sort of combinations of elements, no matter where you find water, it will always be that sort of combination of basically 1 gram of hydrogen for every 8 grams of oxygen. Some other sort of laws, the law of multiple proportions, which was done by Dalton, says that basically when 2 elements form a series of compounds, the ratio masses of the second element that combine with 1 gram of the first element can always be reduced to whole numbers. So for example, as well, if you look at something like NO and NO2, for example, that's basically 1 nitrogen for every 1 oxygen, 1 nitrogen in this case for every 2 oxygens. And again, if we sort of look at the masses here, this is basically 14 grams. This is basically 16 grams. So if you take basically 16 grams for every 1 gram of nitrogen or grams of nitrogen, get sort of a ratio of 1.14. If you do this for NO2, you basically again have 14 grams. 2 oxygens is about 32 grams. So if you take 32 grams and divide it by 1401, so you do that 32 divided by 1401, you'll get a 2.28 in terms of the ratio. If you take those two and divide it, it's basically 2, right? So it basically goes up by a factor of 2 is the proportion there. So when basically atoms come together from different elements or really the same elements, they always really do combine in sort of whole number ratios. You'll never sort of get a half of atom or anything like that. They will always sort of have that whole number sort of situation occurring. Any questions on that there? So speaking of Dalton, let's talk a little bit about some the earlier ideas of an atom. Um, John Dalton was an interesting. Whoops, come here. It was an interesting guy. He showed a lot of unusual talents for math and science. He woke up every day and wrote down the weather. He obviously never got married. But the most important thing really about John Dalton was he did like to go bowling on Thursdays. So when that shows up on the exam, make sure you put the right day, not like Fridays or Sundays or something like that. So he went bowling on Thursday. He wasn't a really good public speaker, but he did a lot of private tutoring. But what he's really known for is he did come up with sort of a definition of what we call atoms, which is known as Dalton's atomic theory. Um, and let's take a look at some of the ideas of Dalton's atomic theory. One of the ideas was that really each element is made up of these tiny particles which are indestructible, these sort of indestructible sort of particles. Um, that is not necessarily correct, as later found out. You can, for example, in nuclear chemistry, you can sort of change elements into other elements and, kind of move them around and stuff like that. But at the time, it was made up of these tiny particles called atoms. And again, sort of this indestructible sort of idea. Another idea of Dalton's atomic theory was that atoms of a given element are identical and that atoms of different elements are different in some fundamental way. This is also another sort of part of Dalton's atomic theory, which was again not so correct in all aspects. Again, the idea here, this is a theory, as we talked about, so maybe not right in all aspects of it. And the part that's not sort of correct anymore is sort of the first sentence here, that elements or atoms of the same element are always going to be identical. So with the idea and sort of the discovery of, as we will talk about, what are known as isotopes. Isotopes are basically the same element, but they do have different masses, which means that if you have an isotope of the same element, those two atoms will not be identical to each other because they do have different masses associated with them. So again, that's another sort of part of Dalton's atomic theory, which was not found to be correct as sort of time went on. The other is correct, part of that, which is atoms of different elements will be different fundamentally. They have different masses, for example, different numbers of protons and neutrons and stuff like that. Another important part of Dalton's atomic theory is that chemical compounds are formed when atoms of different elements combine with one another. A compound is always has the same relative number and types of atoms that are associated with it. So again, this is the idea that basically elements and atoms will come together in these sort of really whole number ratios to form different compounds, and they will be bonded to each other in some aspect. The last part of Dalton's atomic theory is the idea that chemical reactions really only involve the reorganization of atoms and changes in the way that they are bound together. So this is sort of that idea of that conservation of mass as well. We're not going to lose any sort of atoms in a chemical reaction. Basically, we're just going to kind of break all the bonds of everybody that we start with. We're going to reassemble on the other side with some new bonds and make some new compounds along the way. Again, we really have sort of the conservation of the elements because as we'll talk about, as you might know, again, bonding and breaking bonds and making bonds really only involve electrons, which has no effect on the elements that are being present, just allows them to sort of move around and stuff like that. So those are the main points of Dalton's atomic theory. You do need to kind of know those points. And again, atoms themselves are not changed, obviously, in a chemical reaction. All right, so take a moment here and we're looking for which of the following statements are still believed to be true today. So take a moment and see which ones should still be. All right, so looking through these, let's see here. Elements are made up of tiny particles called atoms. That is still correct, right? All atoms of a given element are identical. Is that correct still? That is not correct, right? A given compound always contains the same relative number and types of atoms. That is correct, right? No matter where you get your water, it's always 2 hydrogens and 1 oxygen. Atoms are indestructible. Not so correct. So it looks like number 1 and number 3 are winners there in terms of things that are still correct. Any questions on that? So again, for Dalton's atomic theory, you need to know the different parts of it. You do need to know which parts of like this question are not so correct anymore. And clearly you need to know he went bowling on Thursday, right? So again, make sure you know that. All right. So speaking about some theories and laws and stuff like that, we'll talk about some of these laws a little later on when we get into gases. But we do have some laws like, say, Guy-Lussac's law. He measured kind of pressure and temperature relationship, keeping volume constant. And what he found in that situation was that as the temperature increased, you would see an increase in the pressure. And that's because the gas molecules would be flying around a lot faster, causing a lot more collisions and a lot of increase in the pressure. Our friend Avogadro also has sort of a gas law as well. And his law was that under constant pressure and temperature, the volume of gases contained the same number of particles. So kind of the moles of the gas would be equal to the volumes in a Avogadro sort of situation. So there are certain things like laws, and this, by the way, we'll see it again when we get to the gas chapter. That is Guy-Lussac's law, and this is Avogadro's law. And this is pressure and temperature at 2 different situations, volume and moles, basically, are those things. And again, the relationship here is basically they're sort of proportional there in terms of Avogadro's law. And as we'll talk about when we do get to sort of the gas chapter, you could kind of do stoichiometry and sort of a volume to volume relationship, just like you could kind of do stoichiometry and a mole to mole relationship under those sort of conditions. All right. Get through these pictures here, I think. When we talk about Dalton, as we talked about before here, and as we were mentioning again, this is sort of how he pictured the elements coming together. And again, they could come together in these sort of different proportions. And they're all nitrogen and oxygen. But in certain cases, we have, like we can see here, our nitrogens and our oxygens coming together. We have actually 2 nitrogens coming together. And we can look at the ratio of these guys, kind of like we did earlier. And again, if you do it per, say, gram of nitrogen, you can basically get the ratio of how they come together, like a 1-to-1, a 1-to-2, and in this case, a 2-to-1 sort of situation. All right, so based on Dalton's atomic theory, a lot of sort of ideas were thought of about the atom. The atom, again, was thought of as basically the basic sort of representation of elements that can come into sort of chemical combination. A lot of research and investigations were done through the 20th century. And although atoms are extremely small sort of particles themselves, it was sort of believed and discovered that although they're super small, they do contain even smaller particles that make up atoms. And those are sometimes referred to as subatomic particles. And as you may be familiar with, the 3 subatomic particles are our friends electrons, which are negatively charged, our friends neutrons, which have no charge, and protons, which have positive charges. So this idea that we have these really small sort of particles, which are atoms that are basically make up all the different elements, and they have sort of an internal structure of even the smaller particles. What we're going to again here talk about now is the different sort of experiments that sort of led us to understanding where these particles are in the atom and sort of the overall structure of the atom. So let's take a look at each of these here. So really the first thing that a lot of people sort of looked at or was looked at were electrons. And the idea of electrons and a lot of what happened with electrons really all started with using the cathode ray tubes. And the cathode ray tubes are sometimes abbreviated CRT. And CRT tubes are basically this idea of you have basically like a tube, and there's a positive side and a negative side. And in chemistry, there's a really important idea that's known as basically opposites attract, right? And that means that something that is negative will be attracted to something that is positive. Things that have the same charge do not want to be near each other. They are repelled by one another. So things with a negative and negative charges will really want to try to get away from each other. Things with positive and positive charges will also try to get away from each other. So a CRT basically is a cathode ray tube, is a sort of electrical field, and it shoots really these negatively charged particles. And because they're negatively charged, they are going to be attracted to the positive side of sort of that electrical field. And a lot of times they'll put something on it that fluorescents so you can kind of see where it is hitting. And you may be familiar or have seen a CRT tube. Really old TVs that have like backs on them, not like flat screens or anything like that. You could actually take off the back of a thing, and there's a picture tube in there, which is basically a CRT. Old computer monitors, if you've ever seen one that has, again, like kind of like a big back on it and stuff like that. Those are cathode ray tubes. Obviously, nowadays, none of those monitors or things are those type of things. But those are all CRT type tubes. So it was determined using this sort of CRT tube that J.J. Thomson did a lot of work, and he was able to figure out the charge to mass of an electron. And he basically, and here's a picture of the CRT tube. I knew it was here somewhere. So here's a picture of a CRT tube. And again, this beam here is basically negatively charged electrons. And again, it's going to go to this sort of positive side here, away from the negative side. And here's actually one, I think.
Is a cathode ray or Crookes tube.
Maybe.
It produces a beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
So you can see that beam again is the cathode ray tube, or the cathode ray is called, the negatively charged, basically electrons hitting it. And it is affected, as you can see, by a magnet. And a lot of things with charges, as we'll talk about here, when we talk about sort of these experiments, a lot of times these experiments use a lot of radioactive particles that have charges. And some very common ones are alpha particles, which have positively charged particles, radioactive particles. There's beta particles, which are negatively charged. And there's gamma rays, which basically have kind of no charge. So, they almost symbolize, your protons, electrons, and neutrons. And the reason why they used a lot of these sort of particles in some of these experiments that we'll talk about as we continue on here was the idea that you could affect it by a electrical sort of field. So if you shot a particle, right, and it went through an electrical field and it kind of moved upwards towards the positive side, that particle would have what type of charge? If it moved towards the positive side, it should be opposite would be negative, right? Because it's going to be attracted to the positive side of the field. Just like if you shot a particle and it kind of bent towards the negative side, you would know that that guy probably carrying a more positive charge, as it's obviously going towards the negative side of the electrical field. And same idea if he shot something and it really was unaffected by an electrical field, basically will just go straight through, right? As it's not going to be kind of pulled in either direction to do that. A magnetic field, like we saw with the magnet there, works kind of a similar way. There's a South Pole, North Pole, and it also will affect things that have charges on it. So a lot of electrical fields were used, magnetic sort of ideas there. And again, this idea of these different types of particles. So Thomson, as I mentioned earlier, there used the CRT tube. There he is staring at his tube right there. Bless you. And again, the major thing that came out of Thomson's experiment was the charge to mass of an electron. And he found that the charge to mass of an electron was minus 1.76 times 10 to the 8 coulombs per gram. Coulombs is an electrical charge unit. Hence the charge to grams, which is a unit of mass. So the charge to mass of an electron was discovered doing this experiment. And this was a good sort of step forward in the idea of the sort of idea of what's going on with our electrons. Another really important experiment that sort of went with the idea of Thomson was one that was performed by a guy named Millikan. And Millikan did what is known as the oil drop experiment. And what Millikan was able to basically determine was the mass of an electron. And the oil drop experiment, as we'll see on the next page, is really this idea where they had sort of an electrical field and they shot sort of oil droplets in. And by gravity here, the oil droplets would want to fall. And it would pick up basically some charge as it's falling. And what they were able to really essentially do with the electrical field in this experiment in this chamber is they were able to sort of adjust it in such a way that basically the oil droplet just kind of hung there. It didn't really fall or drop or go anywhere, just kind of hung there. And from that, they were able to, like we said, they're sort of figure out the mass. I'm sorry, sort of be able to figure out the charge of an electron. So sorry, circled the wrong thing. So Millikan figured out the charge of an electron. So what we have here is basically Thomson, who was able to figure out the charge to mass of an electron. We had Millikan, that was able to figure out the charge of an electron from this experiment here. Taking both of those together, if we take the charge of an electron and we divide it by the charge to mass of an electron, charges will cancel, and that will ultimately give us the mass of an electron. So these two experiments really helped us have a better understanding of the mass of an electron. Yeah. Yes. So you should know these people and sort of the experiments that we're talking about now. And here is sort of that experiment there. And go play maybe. Yeah. There we go. So as you can see, they kind of shoot oil droplets in there. It comes down. They're able to adjust that electrical field to keep that sort of oil droplet sort of suspended. And again, this is the charge on an electron that Millikan was able to determine. So again, Thomson using CRT tubes were able to figure out the charge to mass of an electron. Millikan doing the oil drop experiment here is able to figure out the charge of an electron. And again, kind of putting both of those experiments together allows us to understand the mass of an electron. So let's take a look at what that will be here. So the mass of an electron, by doing the calculation, ends up being 9.09 times 10 to the minus 28 grams. That's a large number, small number? It's a really small number. Yeah, that's like 28 places to the left and put zeros. Yeah, I'm gonna move that decimal 28 places and put a bunch of zeros in front of it. All right, so what you need to know again here is Thomson CRT tube, charge to mass of an electron, Millikan oil drop experiment, about to get the charge of an electron, again using both of those together to get the mass of an electron. Any questions on that there? So now that we sort of have an understanding of electrons and a little bit of the property of electrons, obviously there was still this idea that the atom probably had some other sort of characteristics to it. They understood that really the atom was sort of neutral, so it has to have some type of positive sort of aspect to it. So that brings us to really the protons and the nucleus. So by early 1900s, it was definitely understood through these experiments that they did contain electrons atoms. And like I said, they were electrically neutral. So clearly, if electrons are negatively charged and the atom is neutral, there has to be some type of positive component to the atom to really balance out the negative charge of those electrons. So around the turn of the century, the sort of early model of the atom that was proposed was that was done by Thomson. And Thomson came up with this idea that the atom was essentially this sphere of positive charge. So all that positive charge needed to balance out the electrons was really spread out over an entire sphere. And he felt that embedded inside this sphere were these negatively charged electrons. So we have these negatively charged electrons sort of embedded inside. And he also felt that most of the mass of the atom was the electrons. And this is what is sometimes referred to as the Plum Pudding Model. And that's like a English dessert, I believe, pudding with like raisins in it. And the raisins are like the electrons. The pudding is like the positive charge sort of spread out all over the sphere. So this was really sort of the accepted version of the atom based on sort of the information that they knew. It also, again, accounted for the idea that they believed that the atom should be electrically neutral. So we have this sort of positive charge spread out all over. Here's a much prettier picture of that here. Again, all that blue is our positive charge spread out and sort of diffused over the atom, electrons embedded inside. Now, this was sort of really the accepted idea of the atom until really the next major sort of development occurred. And that major development that occurred was done by Rutherford and Geiger and Marston, but mostly referred to as Rutherford's experiment. And Rutherford did an important experiment, which is known as the gold foil experiment. And in the gold foil experiment, he took pieces of gold foil and other metals and he shot these alpha particles at it. So these are, again, these positively charged radioactive particles. They're essentially the helium nucleus is basically what they are. And he shot it at these pieces of gold foil. Now, based on sort of the idea of the plum pudding model, he actually expected certain things to occur when he did this. So if we think about sort of the idea of the atom that we just saw there in this picture, he basically thought that he's going to shoot these alpha particles, which are positively charged. They're heavy and they're obviously moving pretty quickly. He expected these alpha particles to come through, but with some deflection. And that is, if you think about it, right, you're shooting something positive at positive, right? So it is going to really not want to be there, but it is going to be able to punch through because it's heavy and moving pretty quickly. So it's going to be able to punch through, but it's going to kind of reflect itself or deflect itself out of the way. It's sort of the idea that if I take like this paper here, and this is my atom, this is all the positive charge, and I like held one side, somebody else held the other side really tight, and we shot like this pin at it moving really fast, it's probably going to be able to punch through, but as it goes through, right, it's going to kind of deflect a little bit as it tries to punch through that. And that's sort of what Rutherford expected to sort of happen when he did his gold foil experiment, based on the idea that the plum pudding model was correct. And what he actually saw is this.
Co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles. some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them.
So if we look at it here, what they actually saw was, as we saw on that sort of animation, was that most of the particles pretty much sailed through with no problem. But every so often, they did see that these alpha particles would be scattered at these really sort of large angles. Sometimes it would come back even to the source at which it came at. So if pretty much these alpha particles didn't have a problem, as we see here on the detector screen, just kind of sailed right through, that meant that they pretty much hit nothing, right? So like if I threw my pin that way and there's nothing in the way, it's going to have no problem, right? It's just going to sail through and keep going. Now, they did see that every so often, as you can see here and in that animation, you know, they would get reflected or deflected at these really large angles. Some would even head back to sort of the source as well. Now, in order to make these alpha particles, which are really, really positively charged, bounce off at these really large angles, it had to hit something that was what type of charge? Really, really positively charged, right? Because it is positively charged, the alpha particles. The only way to make it bounce off really at really large angles is it had to hit something that was really, really positive to make it bounce off. So the idea here is perhaps maybe the plum pudding model where we have basically our positive charge spread out all over, not so correct. But if I took my positive charge and I folded it just like I could definitely fold positive charge, right? And we keep folding it and keep folding. Was it like 7 times? So you can't fold something anymore, right? And now that we have something like this, and instead of my positive charge being spread out all over the atom, now maybe it's all centralized into here. And now when I throw my pen through it, it obviously is not going to go through, right? It's going to be deflected back because it hits something very, very strongly positive at it. So this was a really big sort of discovery, this experiment based on the plum pudding model. They definitely expected something different to happen. And again, this is why we do experiments, right? So we actually find something else actually occurred in this case. So this was really important that they found that a lot of the particles really had no problem and went undeflected, which meant that, again, instead of the atom having all this positive charge spread out all over it, it had a lot of empty space that's not going to get in the way of anything and going to allow those particles really to travel through. As we just talked about, again, in order to make those alpha particles really bounce off at these really large angles, it definitely had to hit something very, very positive. So the idea here is, as you can see, we sort of has to kind of throw out the plum pudding model and sort of come up with a different model of the atom, which basically accounts for the observations that they saw in the Rutherford's experiment. So this again on the left is what they sort of expected to happen. A lot of deflection as it went through all that kind of positive charge. Again, they saw mostly went through no problem. And again, we have this really concentrated positive sort of charge there in the atom. So coming up with sort of a new sort of definition here, our idea of what the atom is based on Rutherford's experiment is that the atom is pretty much, as it says there, mostly empty space. And again, that is pretty much what accounts for those alpha particles not bouncing off at any angle. It's just really sailing through with no problems. It contains a dense positive core, which is known as the nucleus. Later experiments and such found that in the nucleus, that is where we find our protons and our neutrons. And our protons are positively charged, obviously later determined those particles being there. Neutrons not until like 1930 it was discovered. And the other really major difference between sort of the plum pudding model and really the modern version of the atom, which is the same version that we talk about today, is the idea that most of the mass of the atom is actually the nucleus. So unlike the Plum Pudding Model, where they felt that most of the mass of the atom was the electrons, it's actually the nucleus, that really dense positive core, is where we have most of the mass of the atoms. So the idea is we do have sort of our nucleus, where again later found protons and neutrons are inhabiting. We have electrons out from the nucleus at some distance in that empty space. And by the way, electrons, as we will talk about, do not travel in pretty circles. They travel pretty randomly about the nucleus. So they don't travel in these pretty little circles or orbits or anything like that. They travel pretty randomly. Yes, sir.
So, no, our experiment was the stuff like the discovery of the nucleus.
Yeah, I mean, that's one of the major things that came out of it, and really a revision of really at that point the version of the atom that everybody had in sort of their head that was that Plum Pudding Model, where again that positive charge was really sort of spread out. So really the discovery of the nucleus, and really that's probably where again later on protons, which is that positive charge, is sort of housed, is really a major discovery, along with the idea again that that positive charge is not really spread out, but it's actually mostly empty space, the atom, right? So it's mostly that empty space. Say again?
He kind of said that they revolve around something, which would be
No, so in the Plum Pudding Model is basically the idea that the positive charge was spread out over the entire sphere, and embedded inside there were these sort of electrons moving around. And so the idea is like raisins and like pudding, basically. So electrons kind of are like the raisins in the pudding and stuff like that. Yeah. Yep. Other questions? So for Rutherford, obviously, you need to know the gold foil experiment, what was done, what they thought was going to happen, what actually did happen, and clearly our sort of modern version here of the atom. Any question on that there? All right, so this is just a table of some of the experiments that we talked about, and again, some of the things that came out of those experiments. So a nice little summary type table. We have Thomson getting our charge to mass, excuse me, with the CRT. We have oil drop experiment with Millikan getting our charge, again, allowing us to get the mass of an electron. We have Rutherford's gold foil experiments. And really, we didn't talk too much about it, but prior to the CRT tube, just general gas discharge tubes were used to sort of explore the atom and different parts of it as well. So obviously we have this dense positive core, and it was found that these positively charged particles were referred to as protons, and protons have a mass of 1.67 times 1.67252 times 10 to the minus 24 grams. And if you remember, the electron was in the ballpark of 9.09 times 10 to the minus 28 grams. And as you hopefully know by looking at those two numbers, it is the proton that is much heavier, right, than an electron. When you look at a negative exponent, the smaller negative number is actually the larger number, because you're only going, say, 24 places to the left versus 28 places to the left. So a proton, which is positively charged, it's found in the nucleus, and it has a mass that's about 1,840 times heavier than any electron that's flying around. That also gives the idea or sort of credit to the thought that the most of the mass of the atom is actually the nucleus, because in the nucleus you have protons, which are about 1,800 times heavier than any electron flying around. So that does make sense that most of the mass is going to come up from that nucleus where those protons are found. Now, at this stage, they sort of thought of the atom as the nucleus comprised most of the mass of the atom, but occupied a very small volume of the atom. So in this sense, you could think of the atom as the size of like the Superdome, or a really big, say, football stadium or something like that. And the nucleus is like a small little marble on the 50-yard line. If you've ever been to the Superdome, pretty big. You sit in seats and you feel like you're going to fall out of your seat while you're sitting. but a really big stadium, and really the nucleus is just this really small part of it. So the atom has a lot of open space where those electrons are flying around in. And again, most of the mass of it is all centralized there in sort of that nucleus in the middle. Now, again, it was long believed that in addition to protons and electrons, and especially in addition to sort of protons, there was another sort of particle found in the nucleus. And it really wasn't until a little bit down the road there, 1932, that the neutrons were actually discovered. It's discovered by a guy named Chadwick. And what he did is he did a lot of experiments with beryllium and alpha particles. And what he saw were there was some energy that was coming off that resembled gamma rays. If you remember, gamma rays have no charge. And later experiments show that these are consistent with electrically neutral type of particles that have a mass of 1.67495 times 10 to the minus 24. The reason they go out so many decimal points is that allows actually the neutron to be slightly heavier than the proton. So the neutron is actually slightly heavier than the proton. The neutron is also found in the nucleus. The neutron is also about 1,800 times heavier. So once again, in your nucleus, you have your protons and your neutrons, you have your electrons on the outside. Both of these guys individually are 1,800 times or so heavier than any electron. So once again, that sort of cements the idea that pretty much in your nucleus, you have these really heavy particles, which is going to make pretty much most of the mass of the atom rather than the electrons. So in terms of the particles, neutrons are the heaviest of the three, followed very closely by the protons, and the electrons are much, much lighter of the three sort of subatomic particles. Any questions on that there? So as we can see here from this table, heaviest next and much lighter there. You do not need to know the exact numbers of each of these things, but you do need to know the charges of each of these things, which obviously is positive, negative, no charge. You also need to know the location, so nucleus, right? Out in empty space, and nucleus, right? And obviously, you do need to know which one is the most massive, which is the neutron, followed by the proton, and the electron being the lightest. So you just need to know it in that sort of order, heaviest to lightest, but you don't have to know the exact numbers for our purposes here. Any questions on that there? All right. Any questions on the atom, the experiments? So again, you know those major experiments that we talked about, a little bit about what happened in each of those experiments, sort of the results of those experiments. Any questions on that? Yeah. How do they find the mass of protons? They basically used they come up with basically like a standard to compare it to, and they assign, in most things in chemistry, a lot of things in chemistry, they assign something that's like a standard, and they kind of compare things to. So for example, we'll talk about that idea when we talk about like the atomic mass of elements. So they take like an isotope of carbon, and again, it has a mass of 12, for example. And they go, okay, this guy is only about, this percentage of that carbon 12. So they do like a little math calculation, something like that, something similar to that. Other questions? All right, so as we talked about, the nucleus is small compared to the oversize of the atom. It's extremely dense, and again, accounts for most of the mass of the atom. And again, here's sort of a cross-section of it. This sort of pinkish area is really the empty space, and that's where we tend to find electrons traveling. Now, we have these electrons that are traveling in this sort of empty space. We have overall a positive charge nucleus. Is there going to be attraction between the electrons and the nucleus? There is, right? So that's that opposite attraction that occurs. That's also why electrons just don't like fly away, right? Don't fly off, right? There's that attraction. It kind of pins them to the nucleus. It's also why, as we'll talk about when we get to different chapters as well, why certain types of electrons are involved in bonding, for example, and others are not. So there are certain electrons that are much closer to the nucleus, which are not involved in bonding. And there are certain ones that are further away from the nucleus, which means they're not going to be held as tightly, so they're much easier to be used in bonding and stuff like that. They can be lost, they can be shared in that situation because of the attractive force. So the chemistry of pretty much all atoms, and as we'll talk about in a lot of situations, and pretty much all the situations in this class, which are basic chemical reactions. So in a chemical reaction, pretty much as I mentioned, all you do is break bonds, and then you make some new bonds. And really, bonding is all about electrons. So all of bonding is about those electrons. And you can think about really the model of the atom that we just saw. Electrons are on the outside flying around. So obviously when two atoms come together, it's the electrons that basically kind of come in contact with each other and interact with each other. And again, really the nucleus in a chemical reaction pretty much doesn't get touched. So nothing happens in the nucleus. So protons and neutrons are not changed or anything like that. In a course of a normal chemical reaction. If you take 200B, you'll talk about nuclear chemistry a little bit. And in a nuclear reaction, it's very different. It's all about changing stuff in the nucleus, the protons and neutrons and stuff like that. But in normal chemical reactions, like we talked about in this class, it's all just about the electrons, which means that's really, as we'll talk about, why we do have that kind of conservation of elements. They don't change from the start of the reaction to the end of the reaction, because it's just the electrons and the bonding that's changing. So let's talk about some other sort of aspects of atoms, and that's going to be the atomic number, mass number, and isotopes. So atoms with the same number of protons, but a different number of neutrons are basically what are referred to as being isotopes. Now, because they have different numbers of neutrons, they will have different masses, and that's why that one part of Dalton's atomic theory was not so correct, where he said that all atoms of the same element are identical. So obviously these are all the same element, but they're not identical as they have different numbers of neutrons. And again, that's what sort of made that not so correct. They show identical chemical properties. And again, that's because pretty much all reactions are going to be happening with electrons. So the numbers of neutrons is not going to play too much into a role in terms of the reactions that it will do. In nature, most elements contain a mixture of different isotopes. And as we'll talk about when we get there, in terms of the atomic mass, for example, that you see on the periodic table, it's basically a combination of all the naturally occurring isotopes for a particular element, is how they sort of come up with those sort of masses. So here again are some two isotopes of sodium, and we got 11 protons and 11 protons in sodium, but one has 12 neutrons on the left there, 13 neutrons on the right. Again, the difference in the number of neutrons here is what makes it an isotope of each other. They're both sodium in this case, but it again is that different number of neutrons that we find in the nucleus that make them isotopes of each other. So let's talk a little bit about atomic number, and the atomic number, which is abbreviated with a Z sometimes, is the number of protons in the nucleus of an atom. And that is, by the way, the definition of atomic number is the number of protons. Now, if you do have a neutral atom, clearly in an atom, there's only three particles. There are protons, which are positively charged. There are electrons, which are negatively charged, and there are neutrons that have no charge. So in order for something to be neutral, the number of protons, which are positively charged, would have to also equal the number of electrons, which are negatively charged. So if you're dealing with a neutral atom, the atomic number will also tell you the number of protons, but it will, in that case, give you the number of electrons, as it has to be the same number in order to basically equal 0. But you should note that, and a very common people miss this, which is if you were asked just a straight up question of what is the definition of atomic number, it is only the number of protons. So that is the actual definition of atomic number, is just the number of protons. The side note to that is if it's neutral, it will also give you the number of electrons that that atom has. So for example, if we look at nitrogen, Nitrogen's atomic number is 7, and that means that in nitrogen, it has 7 protons, which are positively charged. It would also have 7 electrons, which are negatively charged, which gives you no charge overall when you look at it. The atomic number can be found right there on the periodic table. It is that number on the top of the symbol. So if you look at the periodic table, the atomic number can be found on the top of the symbol. If you look up nitrogen up there, again, you will see a 7 there. If you look up hydrogen, hydrogen has a 1, which means it has 1 proton, and it should have 1 electron as well. Gives you no charge overall, right? +1 and -1 equals 0 when you add them together. If you take anybody else up there, 6 for carbon. Carbon would have 6 protons, and it would also have 6 electrons, again, giving you no charge overall if you had a neutral carbon atom. If you look at the periodic table and you look at all the numbers that are up there, do any of the numbers repeat? If you have a closer periodic table, you can look at it. Do any of the numbers up on top repeat? They do not. So the atomic number is a really important number because every single element has its own atomic number, which means if you know the atomic number or you know the number of protons, which is essentially the same thing, you know what element you're dealing with. So you would never have a carbon atom with 5 protons because carbon has 6 protons. 5 would be boron, which is right next door to it. So if you know the number of protons or the atomic number, you know the element. That is why when we look at what we saw over here, we know that both of these are sodium because they both have how many protons? They both have 11, which is the number of protons that sodium has. And that is what makes them an isotope of each other. And it is the protons that determines the element that you're dealing with. Neutrons could change, it doesn't matter, but as long as the protons stay the same, they will be the same element. This is also why when we do a chemical reaction, we don't change elements because none of these things in the nucleus gets touched. Protons don't get touched, which means they stay the same beginning and end of the reaction, and only the electrons get played with. So because those protons don't get changed, the element stays the same, and that's why we have to balance an equation when we have an equation to make sure we have the same number of elements on each side. Any questions on that there? Now, another important sort of property of an atom is what is known as the mass number. And the mass number is the number of protons and neutrons there are in an atom. And the mass number is sometimes abbreviated with an A. Now, the mass number is important along with the atomic number because if you take the mass number, which is your protons and neutrons, and you take the atomic number, which is your protons, and you subtract them, protons cancel, that will give you the number of neutrons. So if you take the mass number minus the atomic number, that will calculate you the number of neutrons there are in that particular atom. When you do calculate those things or are asked to give those things, the atomic number, the mass number, the number of protons, electrons, or neutrons, they all need to be positive whole numbers. So they all need to be positive whole numbers. Can't have like a half an electron, a half a neutron, or anything like that. So protons, electrons, neutrons, all whole numbers, mass number, atomic number, also all whole numbers. Can I find on the periodic table the mass number? Is it this number here? The answer is no, it is not this number there. Because one easy way to remember it is the mass number, the atomic number, all those guys need to be whole numbers. If you look on the periodic table, every number below the element is pretty much all decimal numbers, right? They're not whole numbers. So this is the atomic mass, as we'll talk about a little bit later. It is not the mass number. So you could only find the atomic number on the periodic table. The mass number is not found on the periodic table, so do not be the person that writes all the decimals and stuff like that. The reason people sometimes do that is a lot of times the mass number is a number very close to the atomic mass, which is based on protons, electrons, and neutrons, the mass of those things. So a lot of times they're very close numbers, and people sometimes think, oh, they must have just like rounded the number that you find on the periodic table, and that's not the case. So if you're asked any of these type of problems, you'll have enough information to figure out the mass number, the number of neutrons, and stuff like that. But again, the only number that you get from the periodic table is the atomic number, which is the number up on top. Any questions on that there? No. So again, not the mass number. Now, isotopes, as I mentioned before, are really the same element, but they do have different masses. And again, the different masses come from the different numbers of neutrons that they have. As we just talked about, the protons, again, are the most important in terms of what element you're dealing with. There's a couple of ways that we sometimes write sort of formulas for isotopes. We use the symbol. And a lot of times we'll do this method here, where up on top left is the mass number, bottom left is the atomic number. So, for example, if we look at hydrogen, hydrogen has 1 proton and no neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has 1 proton and 1 neutron. And tritium is the radioactive version of hydrogen, has 1 proton and 2 neutrons. So we could write these symbols by doing this. Again, if you're not sure what hydrogen symbol is, but you do know it has 1 proton, you could go to the periodic table and find number 1. And again, when you do, you will see, again, number 1 is H. So we would write H. Atomic number, which is the number of protons, would be 1, bottom left. Our mass number here, 1 plus 0 is 1. That would be our mass number, and that would be our symbol there for hydrogen. Now, if we did it for deuterium, and you may look at it and go, that doesn't sound anything like hydrogen, but we do know it still has 1 proton, which means the atomic number is 1. And again, we would go to the periodic table, and that would still be our symbol. In this case, though, our mass number is going to be 1 plus 1, which is 2, and that would be our symbol there for deuterium. Tritium, again, doesn't sound like hydrogen, but again, we do know it is hydrogen because of the 1 proton that is there, so our symbol will also be hydrogen, or H. And in this case, our mass number would be 1 plus 2 is 3, and here, whoops, 3. And those are our 3 sort of symbols for hydrogen, deuterium, and tritium. And in a sense, if you want the number of neutrons, you basically subtract the top number from the bottom. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2 for the number of neutrons. So basically, you subtract top number from the bottom number, and that will give you your number of neutrons in this case. Any questions on that? Now, sometimes isotopes are written like this, like Cu, say 20. We'll go not 20, 64. There we go. Cu-64. That was the number I was going to spit out there. And in this case, when we look at this number 64, which number is it, you think? That is the mass number. And I know it's the mass number because I could go to the periodic table and find copper. And when I look over there for copper, it is our lucky number 29 there, yeah? And I know that 29 would actually be its atomic number, which means in this case, if we were to write this in the other way, this would be 29, that would be 64 in this case. That means the number of protons in my copper would, for some reason, people want to use the wrong number for this one, as you can see by the scratch out here. Thank you. It should be 29, which is the atomic number, which is our protons, and we'd have equal number of electrons. Other questions on that there? All right, so why don't you try some here and see what you come up with for each of these numbers of protons, electrons, and neutrons. Okay, so let's take a look. We'll start here. CO is cobalt. Again, top number going to be our mass number. Bottom number going to be our atomic number. And again, our number of protons in this case will be 27. I'll grab the right number here. There we go. And we do not see anything written here. So again, we know it is basically neutral, so it has no charge. So we know in that case, hopefully, that we should have an equal number of electrons, which basically gives us 0 for the overall charge. In terms of our number of neutrons, we're going to take our mass number minus our atomic number. And in this case, that will be 60 minus 27, 33, I hope there in that case. Any questions on that first one there? Yeah.
So if there is a charge, then how is
Hold on to that. We'll talk about it in just a second. Okay. Other questions? All right. So let's take a look at the next one, Cl, which is chlorine. And again, we don't see anything written here, so it has no charge. So again, we'll go to our atomic number, which is our bottom one first to get our number of protons, which is 17. That again would mean that we should have an equal number of electrons. That gives us basically no charge. And for our neutrons, once again, going to take our mass number, which is 37 minus 17. Looks like a 20 in this particular case. And lastly here, U, which is uranium, again, starting with the atomic number, that's going to give us our number of protons, which is 92. We'll also have an equal number of electrons there to balance it out. Going to give us 0. And our number of neutrons is a lot, 238 minus 92, I don't know, $1.46, something like that, I think, in this particular case. Any questions on any of those there? Okay, so why don't you try this next one's here. And for each of these, write the symbol with the mass number and the atomic number and see what you come up with. We go to periodic table there. Krypton is Kr. 36, I think. So that's going to give us our symbol here of Kr. 36 that we could get from the periodic table will be our atomic number. That is also our number of protons in this case. So if we take 36 protons plus our number of neutrons that was given to us, that will get us 84 for our mass number. And we will end up with a symbol that looks something like that there. Any questions on that there? Nitrogen there, which was, as we saw earlier, 7 there on the periodic table. So that's going to give us our atomic number. Again, that 7 will also represent the number of protons, which we will just need to add to get to our mass number of 13, which should look something like that there. Lastly, here we're looking for iron. They actually give us the mass number in this case, and they give us, we want the number of protons, neutrons, and electrons. So once again, periodic table is your friend when you're doing this. We'll go there and we find iron as number 26. That once again will represent our atomic number. And they did give us our mass number in this case, which is 56. So the symbol should look something like that. In this case, we do know that it is going to be 26 protons. We'll also have 26 electrons in this case. Again, as we assume it's neutral and has no charge. Obviously, we didn't write anything there. For our number of neutrons, it will be our mass number, which is 56 minus 26. Gonna get us a 30 in that case. Any questions on how to write the symbols with the mass numbers or atomic numbers? All right, so to answer the question that was just asked a second ago, what happens if we do have charges or something does have a charge. So if something does have a charge, that is what is known as ions. And ions are things that have charges. And there's really two types of ions. There are cations, which are positively charged, and there are anions, which are negatively charged. So you can have a positively charged ion, which is a cation. You can have a negatively charged ion, which is a anion. So let's take a look at maybe we'll just steal these two that are on here, I think. And what I'll do is clear that out, get a little bit more room, I think. So let's take a look first off at, we will look at our iron first here. And we just did iron that basically was 5626, and it had no charge. So let's just say in this case that the iron had a +2 charge, right? So in this case, this would be a cation as it is positively charged. So we want to kind of go through our ideas of protons, electrons, and neutrons, for example. So if we start with our protons in this case, it will be 26, right? As that is still the atomic number in this case. And if we wanted our number of neutrons, it would be 56 minus 26, which is still 30 in this case. Now, that would leave you only the electrons as what changes. By the way, when something gains a charge, the only thing that changes is the number of electrons. Why does the number of protons not change? If I change the protons in this, would this still be iron if it's not 26? It would not. So because it still needs to be iron, it still needs to be the same element. It just has a charge. You cannot change the protons, otherwise you change the element. And since neutrons have no charge, they can't affect the charge. So it really is only the electrons that can affect the charge of a particular guy when it does have a charge. So protons will be the same. But in this case, we're looking really for how many negatives will give me a +2 left over. In this case, the number of electrons actually will be 24. If you take 26 positive guys and 24 negative guys, you got 2 left over. And that +2 is where the charge comes from, right? The difference between the protons and the electrons. Questions on that? Now, that is a cation that has a positive charge. What is the difference between the electrons in the guy with a charge and the electrons in the guy without a charge? The one with the positive charge here has less electrons. And that's what a positive charge means. It means it has lost electrons. And the number of the charge is how many electrons it lost from the neutral guy. So +2 means it lost 2 electrons from the neutral. And that is basically what a cation is. It's something that will lose electrons and become positively charged. The reason it again becomes positively charged is pretty much for in the calculation that we see, we have more protons than electrons, right? So we have more positive charge than negative charge. So we got extra positive charge, and that's why you become plus charge. Any questions on that there? Now, if we look at nitrogen here, and we roll with nitrogen, the same guy basically, but we give it a charge of -3. And in this particular case, -3 means that it is an anion, is negatively charged. Once again, the number of protons in this case will be the atomic number, which is 7. Again, it will not change because it is nitrogen still, so we still need the same number of protons that we had previously. The number of neutrons in this case would be 13 minus 7, which would be 6 still. Now, when we look at our electrons, in this case, we will actually have 10 electrons. 10 negatives and 7 positives will leave you a -3 left over, which is essentially where the -3 comes from. You have more electrons in this case than you do protons, so you have a net negative charge overall. When we look at the negatively charged guy versus the positively charged guy, here in this case, the number of protons is 7. Number of electrons is also 7 to give you 0. So the number of electrons in the guy with the negative charge versus the neutral guy, it actually has more electrons. And that is what an anion is. An anion is something that will gain electrons. And when it gains electrons, it becomes negatively charged again because it has more electrons than protons. So in this situation, when something gains a charge and becomes an ion, it is really a result of the electrons in the outside of the atoms. When they come together, they're going to jump from one to the next. So somebody's going to lose a certain number of electrons, somebody else will gain those electrons, and one will become positively charged, one will become negatively charged. That's, for example, what happens when you take a sodium guy and a chlorine. What happens is one of the electrons from the sodium ends up moving on over to the chlorine, and the result of that is sodium lost an electron, becomes positively charged. The chlorine gained an electron, becomes negatively charged. And this is what is referred to as an ionic bond. And the attraction there is actually opposites attract. It is the positive charge of that sodium is attracted to the negative charge of the chlorine, and there's no sharing of electrons. It's actually just that attractive force that results as electrons basically hop off of the sodium and go on to the chlorine in this case. Any questions on that? So if something does have a charge, that is what the negative means. Negative means it gained, and also the number is how many electrons it gained. So positive charge loses electrons, negative charge gains electrons. Protons have to stay the same, otherwise the element changes. So it's only the electrons that change when somebody gains a charge. Any questions on